From the Sudbury experiment, when an electron neutrino interacts with the deuteron, two things can happen. The neutrino can be absorbed and re-emitted, causing the deuteron to split into a neutron and a proton, the neutral current or NC reaction. Or the neutrino can be absorbed and seemingly re-emitted as an electron, causing the deuteron to split into two protons, the charged current or CC reaction. In both cases, the deuteron absorbs the neutrino and the two nucleons forming the deuteron separate. So, the big question then is, what does a neutrino encounter inside a deuteron that causes the reaction to go either neutral current or charged current? An even bigger question may be, why does the neutrino retain its identity in the NC reaction but appears to become an electron in the CC reaction? To answer these questions, a detailed understanding of the structure of the nucleons the neutrino encounters inside the deuteron is needed. For this, we revisit the experiments and analyses that provide insight into the structure of the proton and develop a model of what the neutrinos likely see when they interact with a nucleus. During the time Bacall and Davis were looking at the feasibility of detecting solar neutrinos, not far away at the synchrotron laboratory at Caltech, Murray Gell-Mann, a theoretical physicist, was wrestling with his own particle physics problem. Since the discovery of the positron by another Caltech physicist, Carl Anderson, several elementary particles had been discovered, creating what became known as the particle zoo. To try to make sense of the zoo, in 1961, Gell-Mann and his associates devised a system he called the Eightfold Way. It arranged the particles in octets, organizing the elementary particles in a way similar, in principle, to the way the periodic table organizes the elements. In 1964, Gell-Mann found that he could model hadrons like the proton and the neutron using just three component particles, S, U, and D, if their charges were fractions of the proton and the electron charges. He called the three component particles quarks. The charge of the D or down quark had to be equal to that of the S or strange quark, but the charge of the U or up quark was the strange quark charge plus 1. He set the strange quark charge to minus 1/3, giving the down quark a charge of minus 1/3 and the up quark a charge of plus 2/3. This allowed him to make the proton one down quark and two up quarks, giving it a charge of plus 1, and the neutron one up quark and two down quarks, giving it a charge of 0. With his three quarks and their antiparticles, Gell-Mann could model all of the baryons and all of the mesons known at the time. He was even able to predict the existence of a baryon, the omega minus particle, that would later be discovered. However, although the quark model looked good on paper, it had one big problem. No particles with fractional charges, no quarks, had ever been observed in nature. Consequently, no one, seemingly even Gell-Mann at the time, thought they were real particles. In his paper introducing quarks, Gell-Mann wrote, "It is fun to speculate about the way quarks would behave if they were physical particles of finite mass instead of purely mathematical entities as they would be in the limit of infinite mass." Reflecting on the period, theoretical physicist Arie Bodek, a student at the time, wrote, "But quarks were only considered as one convenient way to model SU3 symmetry." Bodek continued, "Quarks were not considered real particles for very good reasons, such as A. No free quarks were ever observed, B. Quarks had to have fractional 1/3 charges." He concluded, I was told by a leading theoretical physicist that any self-respecting theorist who actually used the quark model in any calculations did it only in the privacy of his own office. I took the advice to heart. No quarks had ever been observed in nature. They were thought of as just a convenient mathematical way to address the particle zoo problem. But by 1967, about 400 miles up Highway 101 at Stanford University, a group of the university's particle physicists were putting the finishing touches on a new particle accelerator at the Stanford Linear Accelerator Center, or SLAC. They partnered with physicists from the Massachusetts Institute of Technology, MIT, and began performing experiments where they fired high-energy electrons at proton targets. These experiments were similar to the ones that revealed the nucleus of the atom, where Ernest Rutherford fired alpha particles at gold foils between 1906 and 1911. The SLAC experiments, called deep inelastic scattering, were done to probe the inside of the proton to presumably show that it was homogeneous and therefore fundamental. However, when the experiments were done, to everyone's surprise, similar to the Rutherford experiments for atoms, they revealed unexpected structure, actual particles, inside the proton. This spurred speculation about what those particles were and sudden renewed interest in Gell-Mann's quark hypothesis. At the heart of the analysis of the Stanford experiment data was a plot of the so-called F2 structure function curve of the proton. F2, derived from the experiment parameters, was plotted as a function of x, the fraction of the proton's momentum. Another Caltech physicist, Richard Feynman, devised an analysis tool he called Parttime Theory that used F2 to determine details about the structure inside the proton. In Parttime Theory, Feynman considered the electron-proton collision from the center of mass perspective, called the infinite momentum frame. There, even though the electron is the moving particle, from its perspective, the proton is moving toward it at near light speed. This causes time dilation within the proton that slows the motion of the particles, the partons, within it. Then, Feynman assumes an impulse approximation where during the collision with the electron, the individual partons are momentarily free within the proton, making the electron-parton scattering elastic. This relays information about the parton's momentum through the electron scattering parameters, which are translated into the F2. For a proton to be made of a finite number of particles, Parttime theory required F2 to peak at the proton momentum fraction x the partons inside the proton carried. The proton momentum fraction x, at which the F2 peaks, is the fraction of the proton's momentum each parton carries. The reciprocal of that momentum fraction is the number of particles the proton is made of. This meant that, if the proton were made of 3 quarks, the structure function curve would peak at about x equals 1/3. When the SLAC data was plotted, the curve did not peak at 1/3. In fact, it did not appear to peak at all. Instead, as the momentum fraction x declined from x equals 1, the F2 value rose from about 0 and continued to rise until x equaled approximately 1/5. Then, it appeared to stay relatively constant as x continued to decline down to about x equals 1/16, the lowest x value measured by SLAC. No peak F2 seemed to rule out the possibility that the proton was made of the 3 particles, the quarks, as Gell-Mann had suggested. But you can never rule anything out in particle physics. Where there is a will, there is a way. And at that point, There was a will, so a way was made. Now that the particles were found, they would be made quarks. In 1969, a pair of Stanford physicists, James Buchanan and Emmanuel Pascos, proposed that a proton containing Gell-Mann's 3 quarks could produce a constant F2 structure function curve from x equals 0 out to x equals 1/5. However, in addition to the 3 quarks, it must also contain a collection, or C, of virtual quark-antiquark pairs. The C would be made of a number of up, down, and strange quark-antiquark pairs that momentarily pop into existence from energy within the proton, then disappear. Gell-Mann's quarks would be the so-called valence quarks, the quarks that define what the particle is. Then, in 1971, Julius Kuti and Victor Weisskopf of MIT analyzed the fraction of proton momentum each type of quark in the proton carried. They showed that, in order for it to be reasonably balanced between the quark types, about 1/3 of the proton momentum had to be carried by uncharged particles called gluons that held the proton together. With the addition of the gluons, the standard model of the proton was formed. Gell-Mann's 3 valence quarks, 2 up and 1 down, a sea of virtual up, down, and strange quark-antiquark pairs, and a collection of chargeless gluons holding it all together. The neutron model is similar to the proton model, except the 3 valence quarks are 2 down quarks and 1 up quark. In the mid-1990s, experiments done at the Hadron Electron Ring Accelerator, or Hera, in Europe, mapped the proton structure function for proton momentum fractions from x equals 0.133 to just under x equals 0.0002. Unlike SLAC, which was a linear accelerator where the electron probe moves and the proton target is stationary, Hera was a ring accelerator where both the electron and the proton move. Accelerator collisions are rated by their center of mass energies. The center of mass energy for an electron-proton collision in a linear accelerator is approximately the square root of 2 times the mass of the proton in energy units times the energy of the electron, while the center of mass energy for a ring accelerator is approximately the square root of 4 times the energy of the proton times the energy of the electron. The maximum SLAC electron energy was 30 GeV, making its center of mass collision energy about 7.5 GeV. The Hera electron energy was 26.7 GeV, and its proton energy was 820 GeV, making its center of mass collision energy 295.9 GeV, about 40 times the SLAC value. To get a center of mass collision energy of 295 GeV in SLAC, it would need an electron energy of over 46,000 GeV. The measure of collision strength typically used to compare experiments is the momentum transfer, or Q squared, from the electron to the proton in units of energy squared. For electron-proton collisions, Q squared at a proton momentum fraction x is 2 times the mass of the proton in energy units times the energy the electron loses during the collision times x. The momentum transfers in the SLAC experiments ranged from about 0.6 GeV squared to about 8 GeV squared, while the Hera Q squareds started at 4.5 GeV squared and went up to 1,600 GeV squared. The collisions in the Hera experiments were overwhelmingly stronger than those in the SLAC experiments. 60% of the SLAC data points had momentum transfers less than 3 GeV squared, and 80% were below 4.5 GeV squared. All of the Hera data points were greater than or equal to 4.5 GeV squared. In the Hera experiments, the proton structure function did not appear to be constant from x equals 0 to x equals 1/5 as assumed from the SLAC data. Instead, it rose significantly from x equals 1/9 as x approached 0. That the F2 did not go to 0 as x approached 0 was viewed as a confirmation of the presence of the C-quark-antiquark pairs and the gluons in the proton, and a validation of the proton model. However, the huge mismatch in the electron-proton collision energies between SLAC and Hera may mean that the data from the two experiments are incompatible. This provides the impetus to look for an alternative model of the proton made from data with similar collision energies in the low X region of the F2 curve. In 1999, the Thomas Jefferson National Accelerator Facility, JLab, performed electron-proton deep inelastic scattering experiments. JLab is a linear accelerator like SLAC. The momentum fractions of the JLab experiments ranged from x equals 0.009 to x equals 0.45, which included the low X range not covered by SLAC, and their momentum transfer values spanned from q squared equals 0.034 GeV squared to q squared equal 2.275 GeV squared, comparable to the range of the SLAC experiment values. The q squareds of all the JLab data points fall within the range of the SLAC momentum transfers. When the JLab data is combined with the SLAC data, the structure function curve rises from near 0 at x equals 1, peaks at about x equals 1/9, then falls toward 0 as x approaches 0. Unlike the combination of SLAC and Hera data, the combined SLAC-JLab data behaves exactly how Parttime Theory predicted a proton made of a finite number of particles would. The F2 peak at x equals 1/9 indicates that the scattering electrons see 9 particles inside the proton, each carrying 1/9 of the proton's total mass. There happens to be 2 known elementary particles that have a mass in the neighborhood of 1/9 of the proton's mass, the pion and the muon. The muon mass of about 207 electron masses is closer to 1/9 the proton's 1,836 electron masses than the pion mass of 273 electron masses. However, with a larger mass, the pions require a larger mass defect to make the proton mass, meaning they would be more tightly bound within the proton than the muons. Also, when protons collide with other particles, they often appear to break up into several positive and negative pions. One argument against the pions is that, based on some analyses of the deep inelastic scattering data, the particles inside the proton appear to be spin 1/2 particles, while the pions are spin 0 particles. However, there is a way to explain why a proton made of pions may still satisfy the spin analyses of the deep inelastic scattering data. The indication of spin 1/2 may be due to the scattering electrons seeing the spin of the whole proton, which is spin 1/2. The plot shown is the test used to determine the spin of the particles inside the proton. If 2 times the momentum fraction x times another structure function F1 divided by F2 is 1, the particles are spin 1/2 particles. If it is less than 1, then they are likely spin 0 particles. The ratio, being scattered about 1 for momentum fractions greater than x equals 0.25, was interpreted to mean the particles forming the proton are spin 1/2 particles. However, the component particles of the proton appear to have a momentum fraction of x equals 0.11, less than the 0.25 where the ratio becomes 1. For the momentum fraction corresponding to the component particles, the ratio is less than 1, and as x approaches 0, appears to be getting smaller. All this could be interpreted as the electron seeing only the spin 1/2 of the whole proton for x greater than 0.25, where they cannot yet see the component particles, but gradually also seeing the spin 0 of the component particles along with the spin 1/2 of the whole proton as x grows smaller than 0.25, where the component particles come into focus. Pions are spin 0 particles.